Okay, we'll start now with chapter 15, well, a little bit after where we left off last time. And this video makes up for missing Monday's lecture. And I will be back in person on Wednesday. But because we lost out on a couple of lectures last week, I'm going to have to post a couple more videos, unfortunately, over the break for you to watch and take notes on between now and next Monday, hopefully. So anyway, this is my second time through these videos. The first time the stupid computer was recording off the wrong camera. So hopefully you'll actually be able to see something this time. And this chapter deals with equilibrium. We've done an experiment with equilibrium in the lab before. And hopefully that experience has given you an introduction to the topic, and hopefully you'll remember some of that, which will help as an introduction. Anyway, equilibrium is a situation in chemistry in which you have forward and reverse reactions occurring at the same time at the same rate. So every time A and B come together to form C and D, somewhere else in the beaker at the same moment, C and D are coming together to form A and B, that kind of thing. It happens because sometimes the products of a reaction are of similar stability to the reactants. And so, you can kind of go back and forth without too much trouble. In most chemical reactions, they will go right the way through to the finish, and all of the limiting reagent will be gone. And at the end, all you'll have will be some products and some of the excess reagent. But in equilibrium, if you put two reactants together, they will react with each other for a while, but then it appears that they just stop reacting with each other because the concentrations don't change anymore. And you'll be left with a little bit of everything. All of the reactants and all of the products will be present to some extent. And that is because as the forward reaction starts, say in a situation where you put the reactants together and you have only reactants and no products, what's going to happen is those reactants are going to start reacting with each other at a relatively fast rate, because there are lots of reactant molecules around and there's really nothing else there to hinder them getting together. And so the initial rate will be fast, but over time, as more and more reactant molecules are converted into product molecules, they'll have a harder time finding each other, and the rate will decline. It'll decrease and then flatten out over time. At the same time, the backwards reaction, where the products come together to form reactants, that starts out really slowly, because at the very beginning of the process, you have only a few reactant molecules in there, and you have lots of, you have very few product molecules in there at the very beginning, and lots of reactant molecules. So the product molecules have a hard time finding each other in order to react with each other and reform the reactants. And so the reverse reaction starts out slowly and gains speed as time goes on. And eventually you get to a point where the forward and reverse reactions are occurring at the same time at the same rate, and that is equilibrium. This kind of equilibrium is called a dynamic equilibrium, because equilibrium means basically everything is sort of equalized out and nothing is changing anymore. But dynamic equilibrium, because at the molecular level, things really are changing, as opposed to a static equilibrium where nothing is changing really, because literally nothing is changing. This is a dynamic equilibrium. An example of an equilibrium reaction that we're going to see a couple of times today is the reaction of hydrogen and nitrogen to form ammonia. And if you put three hydrogen molecules together and one nitrogen molecule together in the presence of an iron catalyst, that's what that says, you get an equilibrium reaction in which some of the hydrogens and nitrogens will come together to form two NH3 molecules. And at the same time, some of the NH3 molecules will start breaking up into H2 and N2. So as I said, if you start this process with only reactants and no products, then the reaction will move toward the right, that is the forward direction, and you'll start forming NH3 ammonia. But eventually ammonia starts decomposing into hydrogen and nitrogen. That would be the reverse reaction. And eventually the rates of the two reactions are equal, and that's equilibrium. The interesting thing about equilibrium is you can approach it from either direction, though. Even if you start out with nothing but ammonia and no hydrogen and nitrogen at all, the ammonia will start breaking up into nitrogen and hydrogen. So the reaction, if you put only product in, will run backwards for a while. And at the same time as more and more ammonia decomposes into hydrogen and nitrogen, some of those hydrogen and nitrogens will come together and start reforming ammonia. And when that happens, you've got equilibrium again. So you can approach equilibrium from, the left-hand side or the right-hand side. Either way, you will end up with the same concentration of products to reactants, no matter how you started out the reaction. And that's one of the other interesting things about equilibrium, is that you not only do you end up with certain concentrations of everything once the reaction reaches equilibrium, but if you take a ratio of the concentration of the products to the concentration of the reactants left over at equilibrium, you will always come up with the same number for that ratio unless you change the temperature. And it'll always be the same number for that ratio for that particular reaction, as long as you don't change the temperature. Sorry. So starting out, and that's actually a lead-in to the idea of equilibrium constants. So any given equilibrium reaction always ends up with the same ratio of products to reactants once it reaches equilibrium at a given temperature. So every reaction has its own characteristic value for this ratio, which is called the equilibrium constant, at a given temperature. The only way you can change the equilibrium constant will be if you change the reaction, obviously, or if you change the temperature significantly. And so again, at equilibrium, the rate of the forward reaction is the same as the rate of the reverse reaction. And the rates can be stated in terms of concentrations. And a quick example would be where the reactions where, say, 2 moles of iodine atoms, and that says G there for gas, will come together to form a mole of iodine, the element I2, also in the gas form, and that is an equilibrium process. And if you look at the forward reaction, it is left to right. So 2 I's in the gas phase go to form I2, also in the gas phase. And since we're looking at just the forward reaction, we can call the rate constant, lowercase k rate constant, as K1. And then the rate for the forward reaction would be K1 times I squared. Since this is each direction of an equilibrium reaction is considered to be an elemental step, you can use the coefficients as exponents in the rate equation when you're dealing with equilibrium. And so the forward rate will be K1 times the concentration of I squared because of the 2. And if you look at the reverse reaction, it's going to be going from right to left. So you're going to start in the reverse reaction, you're going to start out with I2, and it's going to form 2 I's. And this will have a rate constant of K minus 1, just indicating that it's the same reaction as K1, but backwards. And so the rate for the reverse reaction will be K minus 1, rather, times the concentration of I2 to the first power, because the coefficient here for I2 is 1. As I said, though, at equilibrium, the rates are equal. And that means the rate for the forward reaction, K1 times I squared, should be equal to the rate for the reverse reaction, K minus 1 times I2 to the first power. And I wrote something else there, so I scribbled it out. That dot there shouldn't even be there. So it's just concentration of I2. And if you want to sort of segregate the rate constants and the concentrations by themselves, we end up with the situation where the rate constant for the forward reaction over the rate constant for the reverse reaction, that's K1 over K minus 1, will be equal to the concentration of I2 over the concentration of I squared. Okay, that's just how the algebra works out. And that is what's known as the equilibrium constant for the reaction. It is, again, the ratio of the concentration of the products for the overall equilibrium reaction. That would be I2, divided by the concentration of the reactants for the overall equilibrium equation. That would be I. And each of those should be raised to the power of its coefficient in the balanced equation. So I on the bottom here needs to be squared. And so that's what you end up with. Okay, that's KEQ. And so the equilibrium constant is basically just the ratio of the concentration of the products at equilibrium to the concentration of the reactants at equilibrium. The little EQ here just means equilibrium. And sometimes, most of the time, the books don't write the EQ in, but I often do, at least when we're first starting the subject of equilibrium, because I just want to emphasize that you are not using initial concentrations here. You need the equilibrium concentrations of the products and the reactants. And also that means, notice here, if KEQ equals this, then it also equals this. So KEQ is not only concentration of I2 over concentration of I squared, it's also K1 over K minus 1, or the forward rate constant divided by the reverse rate constant. Okay, and that's why it always comes out to the same number every time, because K1, rate constants don't change unless you change the reaction or change the temperature. And so K1 and K minus 1 will always be the same for this reaction at this temperature, and therefore KEQ must always be the same for this reaction at this temperature. Now, the individual concentrations at equilibrium may not be the same, even if you're doing the same reaction at the same temperature. It's the ratio of product to reactant that will be the same every time. Individual concentrations can be different, but they will always end up so that they give you the same number when you take the ratio. Okay, and just as a reminder, in the case of equilibrium constants, you can use the exponents, or you can use the coefficients as exponents. You cannot normally do that with rate equations, but you can do it in equilibrium problems. And so for a hypothetical reaction where you have A moles of A and B moles of B producing C moles of C and D moles of D, your KEQ for this reaction would be the concentration of C to the little c power times the concentration of D to the little d power over concentration of A to the little a power times the concentration of B to the little b power. And all of these need to be equilibrium concentrations again. That's why I wrote EQ over here, but it gets a little crowded because this camera's resolution is not as good as it could be. So I didn't want to mess things up too much. So that's how you set up the equilibrium constant expression. And it's also known as the law of mass action. And setting it up is usually not very difficult. It's sometimes finding the numbers to put in here for the concentrations. That will often be the hard part. Okay. So I just want to say that equilibrium constants include the concentrations of gases and aqueous solutions, but KEQ equations do not include the concentrations of solids or pure liquids. The idea is that the concentration of the solid of the pure liquid will be incorporated into the equilibrium constant. And it's really hard to measure the concentrations of solids and pure liquids too. And so this way you don't have to measure them, you just leave them out. You can also use partial pressures for gases, but you can only do that in cases where all of the reactants and products are gases. And it will give you a different number than using the concentrations that it gives you. But again, that equilibrium constant in terms of partial pressure will always be the same for that reaction at that temperature. It won't be the same number as equilibrium constant in terms of concentrations, but it will always be the same. And there is an easy formula for converting back and forth between equilibrium constants in terms of concentration versus equilibrium constants in terms of partial pressures, which we'll get to a little bit later. So right now, a quick example where you have PCl5 in equilibrium with PCl3 plus Cl2. And they just want you to write the equilibrium constant expression for that. And so KEQ, and the book usually just calls this capital K, but since sometimes it's hard to tell whether it's a capital K or a lowercase k when you're writing by hand, I will very often put the EQ after it. And so KEQ, it will be products over reactants. All the coefficients here are 1, so all the exponents will be 1. And it's just concentration of PCl3 times concentration of Cl2 over the concentration of PCl5. In this case, this is a little harder because you've got 2H2O, which is a pure liquid, in equilibrium with 2 H pluses, which are aqueous, and 2 OH minuses, which are aqueous. And so the KEQ for this equation will be H concentration of H plus squared times concentration of OH minus squared, and that's it. The H2O being a pure liquid does not appear in the KEQ expression, so you just ignore it. Okay, so that's something you have to watch out for. Pure liquids and pure solids don't appear in the KEQ expression. Also, the magnitude of the KEQ can tell you a lot about a reaction. One of the reasons that we're interested in equilibrium constants at all is that it gives you an idea of how far towards completion the reaction goes. If you have a chemical reaction that goes fully to completion, that means it uses up all of the limiting reagent and you end up with nothing but product and excess reagent. If you try to write something similar to an equilibrium constant for a reaction like that, that is concentration of the products over the concentration of the reactants, once you get to a point where the concentrations aren't changing anymore, then one of those concentrations in the denominator, the reactant concentrations, one of those concentrations is going to be 0 because the limiting reagent is gone. Nothing is left. And so you would be dividing by 0. And mathematically, situations like that are usually considered to be equivalent to infinity. And so you could think of the KEQ, not really an equilibrium constant, but say the ratio of products to leftover reactants in a reaction that goes to fully to completion as being infinity. In other words, infinitely large. And with an equilibrium type reaction, the value of KEQ basically tells you how close you come to that situation. Basically, the bigger the value for KEQ, the closer the reaction comes to going to completion. There are some reactions with KEQs in the neighborhood of 10 to the 30th power, which is a really, really, really freaking big number. And those reactions come very close to coming to completion, but not totally, but very close. On the other hand, you have other chemical reactions that can have KEQ values in the neighborhood of 10 to the minus 30 power. And those are reactions that barely occur at all. At equilibrium, you would have practically no products and practically all reactants left over. The sort of cutoff value for KEQ is 1. So basically, if KEQ is greater than 1, then what that means is that the products are favored. In other words, you end up with more products at equilibrium than reactants. Or you could also say that the forward reaction or the right hand direction reaction would be favored. Sometimes we denote a situation like that with the double arrows where the arrow pointing right is much bigger than the arrow pointing left. Sometimes we do this if we want to sort of convey that situation without actually putting down the number. So this is kind of a qualitative way of saying that the KEQ is much greater than 1. If the KEQ is less than 1, then that means that you've got mostly reactants left over equilibrium and not much in the way of products at equilibrium. And what this means is that the reactants are favored, or you could say that the reverse reaction is favored. And sometimes we write the arrows with the arrow pointing left being bigger than the arrow pointing right, just to say that the reaction mostly goes this way and only a little bit that way. And then finally, if KEQ is equal to 1 or very close to 1, then we would say that you have about equivalent amounts of reactant and products at equilibrium. Then neither direction is really favored significantly over the other direction. And in that case, you would just write the two arrows the same size. Now, of course, you can write the two arrows the same size for any equilibrium reaction. It's just that if you write it this way or this way for one of these cases, it conveys more information than it would if you just wrote the arrows the same size. But it wouldn't be wrong to write the arrows the same size in these two situations here. But it would be wrong not to make them the same size if KEQ is equal to 1 or close to 1. Okay, so an example here is 15.2, where we have a couple reactions and they give us a value for the KEQ, and they ask us, would the forward reaction or the reverse reaction be favored? So this first reaction here, and in this case, it doesn't really even matter what the reaction is. If they give you the value for KEQ, all you have to do is look at that to tell which direction of the reaction is favored. If KEQ is 1.1 times 10 to the 7th power, 10 to the 7th power is quite a bit bigger than 1. And so that would mean that the forward reaction or the product direction would be favored. And if you wanted to draw the arrows different sizes, you draw the one pointing to the right being bigger. For the second reaction, the KEQ is 2.99 times 10 to the minus 7. And 10 to the minus 7 is quite a bit smaller than 1. And so in this case, the reverse reaction or the reactants would be favored. And if you want to draw the arrows different sizes, you draw the one pointing to the left being bigger. And in the third example, the KEQ is 2.4 times 10 to the minus 4. And again, 10 to the minus 4 is way less than 1. So the reverse reaction or reactants would be favored. Now, if you want to use partial pressures instead of concentrations, we often refer to KEQ calculated in terms of partial pressures as KP, with the P standing for partial pressures. The alternative would be KC, or equilibrium constant in terms of concentration, but we usually do the equilibrium constant in terms of concentration. So we often just leave the C out and just call the equilibrium constant in terms of concentration just capital K or KEQ. But if it's in terms of partial pressures, then we specify that it's KP. Okay, and so if we have a reaction where the reactants and products are all gases, like this one, where two COs, two carbon monoxides, come together with one oxygen to form two carbon dioxides. Those are all gases. So we can do the equilibrium constant in terms of concentrations. That would be concentration of CO2 squared, because there's a 2 here in front of it, over the concentration of CO squared times the concentration of O2. If you do it in terms of partial pressures, then it's going to be partial pressure of CO2 squared over the partial pressure of carbon monoxide squared times the partial pressure of O2. So you do the same things to the pressures in terms of exponents as you would do with concentrations. Now, to convert from one to the other, because as I said, these two would not give you the same value, although this one would always be the same for this reaction at whatever temperature it's at, and this one would also always be the same for this reaction at this temperature. It's just that this and this would not be the same number. And so you can easily convert between the two by using a rearrangement of the ideal gas law. If you remember that PV equals nRT is the ideal gas law, if you rearrange this to give you N over V, you get N over V is equal to P over RT. N over V N being number of moles, and V rather being volume in liters, N over V is molarity. So molarity is P of a gas is P over RT. And the difference between Kc and Kp is that we're using pressure in one and molarity in the other. And so you can use this term here, P over RT, to convert from Kc to Kp and back and forth. So Kc is equal to Kp times 1 over RT. I'm going to write that again because it didn't come out too clearly. Okay. So Kc is equal to Kp times 1 over RT to the delta N power. What delta N means is what I wrote here in more detail. In this hypothetical reaction here, A moles of A plus B moles of B go to C moles of C plus D moles of D. Delta N would be C plus little d minus little a plus little b. Or in other words, total moles of gaseous product minus total moles of reactants that are gases. And that's what we mean by delta N. Delta N is delta N, oops, there it is. Delta N is the total number of moles of gas in the product minus the total number of moles of gas in the reactants. It only counts moles of gas though. Well, you shouldn't be using Kp if, if there's anything other than gases present anyway. But just remember, you're only counting moles of gas here. And going the other way around is very similar. Kp is equal to Kc times RT to the delta N power. Okay. All right, so there's a question where we convert from one to the other. For the reaction, again, of ammonia, forming ammonia from nitrogen and hydrogen, we're given the Kp being 6.8 times 10 to the 5th at 25 degrees Celsius. And one reason we're seeing the same reaction with different values for the equilibrium constant is that, notice that it's at different temperatures. And so again, equilibrium constant changes if the temperature changes. So at 25 Celsius, the equilibrium constant for this reaction in terms of pressures is 6.8 times 10 to the 5th. They want to know what is Kc in terms of concentrations. Well, that's just going to be Kp times 1 over RT to the delta N power. So that's 6.8 times 10 to the 5th times 1 over RT. R, it's kind of blurry there, but R is the gas constant, 0.082057. And the units being liter atmospheres over moles kelvins. And T is the temperature, but it does have to be in kelvins. So 25 Celsius is 298 Kelvin. And delta N will be number of moles of gas in the products minus number of moles of gas in the reactants. So 2 moles of gas in the product, and in the reactants, you've got 1 and 3 or 4 moles of gas. So delta N is 2 minus 4 or minus 2. All right, so when you work all of that out, you get 4.067 times 10 to the 8th. And that will be Kc. And notice how, the value of Kp and Kc are quite different from each other. But that's because you're using pressures for one and concentrations for the other. But this will always be Kc for this reaction at 25 degrees Celsius. And this will always be Kp for this reaction at 25 degrees Celsius. That's what doesn't change. Okay, I see we've been going half an hour. I want to stop now so the videos won't be too big, but there will be a second installment, so stay tuned. That'll be part 2, and we'll pick up with use and calculation of KEQ when we resume.